Welcome to another episode of G Fun Facts Online. Today we are discussing a monumental shift in environmental science, a turning point that future generations may look back on as the moment we finally learn to clean up our own mess. We are talking about the end of the era of the forever chemical. For nearly a century, humanity has been mass-producing a class of synthetic compounds so resilient that nature literally had no answer for them. You know them as PFAS, or per and polyfluoroalkyl substances. They gained the moniker forever chemicals because of one specific atomic connection, the carbon-fluorine bond. This is the strongest single bond in organic chemistry. It is the reason your frying pan is non-stick. It is the reason your rain jacket sheds water. But it is also the reason why, until recently, these toxic compounds accumulated in our blood, our soil, and our water, with no practical way to destroy them. They were, for all intents and purposes, immortal. But in late 2024 and throughout 2025, the narrative changed. A series of catalytic breakthroughs emerged from laboratories across the globe, from the University of British Columbia to Yale, and most notably, Goethe University Frankfurt. These innovations have given rise to a new class of destruction technology that scientists are colloquially calling the Fluorine Guillotine. This is not just an incremental improvement, this is a paradigm shift. Unlike previous methods that required incinerating water at temperatures rivaling the surface of the sun, these new catalysts act as molecular executioners. They grab the PFAS molecule, position that unbreakably strong carbon-fluorine bond, and sever it with surgical precision. And the most incredible part, they are doing this often, at room temperature, and in a matter of seconds. To truly understand the magnitude of this breakthrough, we first need to respect the enemy. We have to understand why this carbon-fluorine bond is the chemical equivalent of the shield of Achilles. Fluorine is the most electronegative element in the periodic table. In simple terms, this means it holds onto its electrons with a jealous, iron grip. When it bonds to carbon, it pulls electron density toward itself, creating a short, incredibly tight electrostatic attraction that acts like armor. In nature, this bond is incredibly rare. But in industry, it is prized. It resists heat, it resists acid, it resists oil and water. When we created Teflon and firefighting foams, we essentially flooded the planet with microscopic armor plating. The problem is that our conventional water treatment methods, like activated carbon filtration, do not destroy PFAS. They merely move them from the water to a filter, and that filter then becomes hazardous waste. The brute force solution has always been incineration, but that requires temperatures above 1000 degrees Celsius. If the fire is not hot enough, the PFAS molecules do not break. They simply vaporize and rain back down on neighboring communities. We did not need a bigger fire. We needed a sniper. We needed a catalyst that could pick the lock, rather than trying to blow up the door. And that brings us to the first major breakthrough in this new arsenal, the Boron Blade. This development comes from Goethe University Frankfurt, specifically a landmark 2025 study, led by a team under Professor Matthias Wagner. Historically, chemists assumed that breaking the carbon-fluorine bond required heavy, expensive transition metals like iridium, rhodium, or platinum. While effective, these metals are rare, costly, and toxic in their own right. Using them to clean up pollution is a bit of a paradox. The Goethe team, however, defied conventional wisdom. They developed a metal-free catalyst based on boron. Now the innovation here lies in the architecture of the catalyst. The team embedded two boron atoms into a rigid carbon framework. Boron acts as a Lewis acid, which simply means it is hungry for electrons. By locking two boron atoms in a specific geometric pincer, the catalyst forces them to work in tandem. When a PFAS molecule approaches, the boron atoms grab the fluorine, exerting a tremendous tug-of-war force that snaps the bond. The results were startling. The reaction occurred at room temperature and destroyed the PFAS molecules in seconds. As Christoph Buch, the study's lead researcher, explained, to break these bonds, we need electrons. Their boron cage transfers these electrons with exceptional efficiency, turning the terrifying stability of the bond into a vulnerability. By eliminating the need for precious metals, this boron blade offers a path to industrial scalability that was previously economically impossible. But breaking the molecule is only half the battle. The other half is finding it. This brings us to the University of British Columbia and their trap and zap solution. One of the biggest challenges in cleaning water is that PFAS are often present in low concentrations. Finding a few parts per trillion is like finding a specific grain of sand on a beach. In 2024 and 2025, UBC researchers, led by Dr. Johann Foster, developed a system to solve this dilution problem. Their solution is elegantly low-tech in origin, but high-tech in function. They started with biochar. This is essentially charcoal made from forest waste and wood chips. They doped this carbon skeleton with small amounts of iron oxide, which is just rust, to create a hybrid photocatalyst. The process works in two distinct stages. First is the trap. The porous carbon acts like a sponge, soaking up huge volumes of water and selectively latching onto the hydrophobic tails of PFAS molecules. This concentrates the chemical contaminants on the surface of the filter. Once they are trapped, we move to stage 2, the zap. When exposed to UV light, even low-intensity light comparable to a cloudy day, the iron oxide acts as a photocatalyst. It generates reactive radicals that attack the now captive PFAS molecules, slicing through the carbon-fluorine bonds and mineralizing them into harmless salts and carbon dioxide. As Dr. Foster noted, their system works better with light, but it even works in the dark to some extent. This bio-derived approach transforms a waste product like wood chips into a weapon against pollution, offering a sustainable, closed-loop solution for municipal water treatment plants. Now, we cannot talk about this arms race against pollution without mentioning the role of Yale University. Their recent planetary solutions initiatives have pivoted toward something called plasmonic-enhanced catalysis. This sounds complex, but the concept is brilliant. The Yale approach utilizes nanoparticles of Earth-abundant metals, like cobalt and iron, that are engineered to resonate with light. When light hits these nanoparticles, it creates a plasmon, which is a collective oscillation of electrons that concentrates energy into incredibly hot, localized spots on the catalyst surface. Think of it as using a magnifying glass to burn a leaf, but on a molecular scale. When a PFAS molecule drifts near one of these hotspots, the concentrated energy overwhelms the bond, shattering it. This method allows the reaction to proceed without heating the entire volume of water, saving massive amounts of energy. It represents the sophistication of the Fluorine Guillotine, using physics to amplify the chemical power of cheap metals, making iridium-quality performance accessible without the iridium price tag. So how exactly does the guillotine fall? Across all these technologies, whether it is the Boron Blade or the plasmonic edge, the mechanism shares a common logic. First, adsorption. The catalyst must attract the PFAS molecule. Since PFAS has a water-hating tail, the catalyst surfaces are designed to be sticky to these tails, pulling them out of the water and pinning them in place. Second, activation. The catalyst weakens the bond. In the Goethe model, this is done by electron deficiency. In the Yale models, it is often done by injecting high-energy electrons. Third, cleavage. Once the bond is destabilized, a reactive species, often a hydrogen atom or a free radical, slams into the carbon atom, displacing the fluorine. And finally, mineralization. The fluorine atom is released as a safe fluoride ion, the same stuff in your toothpaste, and the carbon backbone creates small amounts of CO2. The forever chemical becomes a never chemical. As we move through 2025 and into 2026, the question is shifting from, is it possible, to, is it scalable? The breakthrough at Rice University in late 2025 exemplified this shift. They utilized a layered double hydroxide material, a clay-like structure that could capture PFAS 1,000 times better than carbon filters. Crucially, they found that heating this material after it was full didn't just release the PFAS, it destroyed them, and the material could be reused. This regenerative capacity is the holy grail for water treatment facilities that cannot afford to constantly buy new filters. Current pilot programs are already integrating these technologies into mobile treatment units. Imagine a truck-sized shipping container that pulls up to a contaminated site, pumps the groundwater through a series of catalytic reactors, and discharges clean water back into the aquifer, leaving behind nothing but a small pile of harmless salts. The psychological impact of these discoveries is as significant as the chemical one. For decades, the narrative around PFAS was one of despair, the idea that we had permanently poisoned the planetary bloodstream. The Fluorine Guillotine changes that story. It proves that even the strongest chemical bond in nature is not invincible against human ingenuity. We are no longer fighting a defensive war, trying to filter and store these poisons in landfills for future generations to worry about. We are going on the offensive. The blade is sharp, the chemistry is sound, and the guillotine is ready to drop. Thank you for listening to G Fun Facts Online.